Hello there! In this video, on a very hot day in Berlin, I would like to talk about a topic which is not really hot but deserves way more attention, in my opinion. And I would like to talk about SQL and, in particular, how do we transform a human language, a human phrase, into a SQL query. And in the previous video, I showed you how we can use a large language model to talk human language to a database. It was Iceberg, MCP, Kafka, and Claude Desktop. And those technologies are deterministic. Usually, they don't bring us a lot of problems. But the key component of how well that analytical task can be performed depends on how well a large language model will be able to translate that human request into a SQL query or a sequence of SQL queries to achieve the goal of that human being. So in this video, let's look how exactly we translate natural language into a SQL query. What challenges are we running into? How can we measure the success? And what kind of benchmarks do we use? What kind of benchmarks exist to evaluate how well an LLM in particular can do that? And also examples how right now it is done in production based on some things which I have found in the internet. We will cover this recent paper, which is actually a survey which will give us a scientific side of the things. Then we will go into a more practical aspect, and I found this really nice article by Adnat Basood. This is really a lot of useful information. Then we will look at the Uber's project Query GPT, which is actually approaches translating natural language into SQL, and we will check two benchmarks, Spider and Bird Bench, just to see what kind of solutions here we have which are winning right now the battle of translating natural language into a SQL query. My context window is somewhat shorter than the one from LLM, so I actually have these PDFs with some notes from my side from all the resources which I used. So starting with the definition of the problem and the background. So indeed we have this challenge of translating just a human phrase. For example, find the names of all customers who checked out books on exactly 3 different genres on Labor Day in 2023. And they look into this problem, they approach it from the human workflow first. They point out some challenges of the context and the information. For example, Labor Day stands for May 1st. So in different countries, Labor Day will be on different dates. So without knowing that information, a large language model can get confused because it doesn't know about which country we are talking about. And this is a challenge number 1. We have a couple of uncertainties here, the lexical one and the syntactic one. So a single word can have multiple meanings, and also the sentence can be parsed in multiple ways. For example, here is a given example. Mary saw the man with the telescope. And then we also have under specification as a third example. That was about this Labor Day in difference in US versus China. The second big challenge is the complexity of the database to which the query later should be made, and the knowledge of the schema of that database by a large language model. In short, we can have hundreds of tables, and the schema can be quite complex. Then there can be ambiguous values and attributes for the model to identify what exactly is the best mapping from the request by the human being into a SQL and what properties should be used. Then the knowledge of the domain-specific attributes and the rest. And also a lot of dirty values, or like not really dirty values, but maybe values or columns in the database which we don't need, or they are duplicated or inconsistent, like how to more or less approach that database with a lot of mass And when, as a database engineer, they might know the nuances of that particular database and which columns actually make sense and which are necessary. But for LLM, it will need that additional context, which values it must take from the data and which values are safe to skip. Then the next challenge, which is probably the most obvious one, is the process of actually translating the text into SQL query. And that will require the strict rules of the SQL to be followed. So depending on the flavor of the database, depending on the schema of the database, LLM will have to write pretty strict SQL query so that SQL query can be successfully executed by that database. And then the last but not the least challenge is that we want to make everything to be cost and time efficient. So there are bigger models which can actually handle these challenges better, but they are more expensive and they take more time for the solution. And what we want to have is the shortest possible, most efficient answer which is trustworthy and which can be run then by the SQL engine and can bring the correct results. To give a better understanding of where we stand over time, this paper gives us a timeline from 2004 till 2025. Notably, you can see that actually they squeeze the time between 2004 and 2016. Anyway, so we have 4 groups of different methods which we use to translate text to SQL. We have this rule-based methods which were from 2004 till approximately maybe 2017 used, then they diminish. Then we have neural network-based methods. Then we have pre-trained language model-based methods. And here on the timeline, you can actually see that in 2018, we actually got a transformer and then BERT and then T5. And that, I believe, even though it's very difficult to say, that actually gets into the gap of, into the bag of pre-trained language model-based methods. And finally, the latest and the most frequently used approach is actually the LLM-based methods over here. So we have ChatGPT, GPT-4, Llama, GPT-4o, so all of those. Also, here they noted the benchmarks which have been used over the time. So we have the first one is WikiSQL, then we have Spider, we have some other evolutions and also the Spider scene, and then BERT and MBQT. So out of those, let me see. So the Spider is kind of a bit older right now, so I will look a bit less into that, but you can actually look into the code, and there is the leaderboard of the models, how they are doing. They recently include also Spider 2.0 DBT. And here is a GitHub repository where you can actually see more information about that particular benchmark. The more recent benchmark is BERT. So BERT contains over 12,000 question SQL pairs, and it includes 95 big databases. So you can download the train set and dev set. There is also for the at the moment on the top of the leaderboard this Ask Data plus GPT-4o, and you can check the paper which they have to understand a bit more how exactly they have achieved and what kind of techniques they have used to translate those text into SQL queries. But these benchmarks, they are actually, in my opinion, that's the best showcase of how well the translation is happening and where right now large language models are comparing to human beings. So here, for example, the human performance to the test data is almost 93% versus the best combination of LLM plus extra algorithms achieves 77%. So it's not bad, but there is still a gap between those two. Now let's talk about the tools we employ to understand the schema, or kind of to map the natural language request to the schema of the database, so that later the model can write a query which uses properly those tables and relationships between the tables for that query. And there has been quite an evolution how exactly we are doing that. At first, there was the usage of what is called string matching based schema linking. So the whole thing is called schema linking. And the first approach, or kind of an old approach, is string matching based. So here we just look for similarity search. So we look at the schema, we look at the user query, and we see what is the similarity in the words, so that we can determine which tables and columns are relevant to that particular query we want to write. Obviously, this is quite vague, and with synonyms and with other things, it's not really the best approach. Try to guess what properties we actually need out of the schema. So even though later we will see that similarity search is still used, this whole approach is a bit outdated. Then we have the neural network based schema linking. This is where we are using deep neural networks, so they are trained to kind of trying to predict the schema, or kind of to get the most out of the schema based on that the request from the user. This is kind of a step forward. However, the most frequently what we use right now is in context learning for schema linking, which is actually our large language models, GPT and the rest. So here, for example, some examples used zero-shot prompts with GPT 3.5. But also we can use multi-agent collaborative frameworks where we have multiple agents. We have the selector agent, and that particular one was only activated when the database schema prompt exceeded the specified length. And this is, and especially if we are talking about some older models, and even current ones, we have actually this issue with the amount of context which LLMs can process. So if we have a pretty big schema and a database with a lot of tables, and a lot of those tables have a lot of columns and all that information, it might actually exceed the context window which we have for that model, which actually raises the issue. So even though this approach of using an LLM for schema linking is probably the most efficient one, it still has challenges due to the inherent limitation of LLMs. Then we have this additional information acquisition. This is about domain knowledge, as well as maybe some examples of the SQL queries or some other additional information about this particular database. We will see this in the Uber example because they are actually using this quite extensively. Among the most notable, this is retrieval augmented generation, where we are using the similarity search and we are adding that additional context into our queries. Then in the conversation about translating text to SQL, we have the encoding strategy. That's where we are actually taking the information from the user, whatever user has typed, what they are looking for, and then we're translating that in the language of the model. And there are different approaches. There is a sequential encoding strategy, there is a graph-based encoding strategy, separate encoding strategies. They all have pros and cons. Then there is a decoding strategy, and decoding strategy is mostly like taking the kind of the knowledge which model inside of it came up with, and then decoding into a SQL response. And here there are also a number of algorithms such as greedy search-based decoding strategy, and apparently this is where the GPT models are using this greedy search-based decoding, but it's not the most efficient. They also mention this constraint-aware incremental decoding strategy, which I believe they state that's the best one. And also there is this beam search-based decoding strategy. This is a bit too in-depth, so I am not going to step here for longer. But in general, there are different strategies. How exactly then the model translate its findings into the SQL itself. And some methods, they require some additional computational overhead. However, they will produce a better result. And notably, the GPT models are not using the most efficient way of doing this. So also the potential for improvement, I guess. Or maybe it's also like the maybe a benefit of using specialized model which just uses GPT maybe as a basis. Then when it comes to the prompt and generally how a large language model processes the request from the user and what kind of how exactly we are giving to the model step by step or as a whole chunk that task, it also plays a huge role. So here we have the chapter for task specific prompt strategy, where we have unsurprisingly chain of thought prompting, which is quite effective, where the model will try to uncover step by step what to do next. Of course, if model makes an error, that additional evolution will be also going to the wrong direction. So there are some risks. However, this is probably, in my opinion, the most effective way of doing the prompting. And here they also mention multi-agent system, where it's kind of a collaborative approach, and then specialized agents will take care of different parts of constructing the SQL or understanding the schema of the database and then do it step by step. Then an alternative to the chain of thought is actually the decomposition strategy, where we split the task into subtasks. In the composition strategy, more or less, we define the plan for the model in advance, whereas in chain of thought, we let the model evolve that plan as it goes. It has pros and cons for each of those. Then another interesting point from this paper is the existence of this intermediate representation during the process of text to SQL translation, so that we are not exactly from the first try to translate text to SQL, but we have some kind of an in the middle representation. Here is a kind of examples. So we can just simplify the whole query, or we can create this draft of the query where you have these placeholders, and then actually you add the information into placeholders later. So this is something I find quite interesting. So again, we are trying to divide a bigger task into smaller tasks, which again, more specific, and more specific task you give to LLMs, the better response you get. So dividing this into sequence of those smaller tasks to figure out which column to use, which table, and so on, might be more efficient. And then last point from this paper, which I find valuable, is talking about of post-processing strategies and the correction of the SQL. And here they actually make a good point that it is easier to fix syntax errors, but a lot of methods actually overlook semantic errors. So like the syntax errors you can correct in the SQL, but if you are missing semantic errors and you just retrieving some really wrong information and do incorrect table joins and wrong conditions, those are more difficult to fix, and those are way more dangerous. Now, this is scientific part. Let's move on and look at an article which I think describes quite well where we stand right now from the practical point of view and where we are moving. So the links, by the way, to all the materials you can find in the description box below. But this particular article I really enjoyed reading. So it starts with a nice argumentation why natural language to SQL is important, but then actually gives a couple of good examples of existing systems which approach this problem and which create architectures. And the first one is Query GPT from Uber. And this one, I think it's worth even reading the complete article where Uber is describing how exactly they came up with this solution. And they actually state that they have a huge amount of data. So they actually perform on their data platform approximately 1.2 million interactive queries each month, and each query can take to a person to write that query around 10 minutes. And they say that using this query GPT, which they created, brought that time into less than 3 minutes, which is a huge win for them. So they started doing this during the hackathon, and they iterated over different versions of this algorithm. And what I found quite interesting is that they actually use retrieval augmented generation quite a lot for translating text to SQL. And I'm like, yeah, why would they do it? And the thing is, they have a really good reason. The whole translation of the text to SQL works like a charm if you just have one table or two tables. But once you have actually hundreds of those tables and you have different domains, it's actually quite difficult to fit everything into that context window for the model, and also model can get quite confused. So that's why they're actually using retrieval augmented generation to figure out the domain. But even before that, so they are talking about several iterations of their query GPT. And the first version used a very simple RAG to get the samples of the queries. And they would take the prompt, they would vectorize the prompt like we usually use in similarity search, and then do the similarity search, k nearest neighbors search, to get 3 relevant tables and 7 relevant SQL samples. And these SQL queries were supposed to provide the LLM guidance on how to use the table and schemas. On top of it, they included the custom instructions on how exactly to treat the data. Here, for example, they have date functions like date trunc and date add can only be used with timestamps. And some other functions, concat, a substring, can only be used on strings. Then they would wrap everything which they got, those examples of the SQL queries, the user request with the natural language, the relevant schema samples, all those business instructions, and they would send that request to an LLM, and they would ask for 2 different chunks: the SQL query itself, which we need, and the explanation for that query. And this is actually the example you can see here. So they have this SQL query, the select count star with all the details and the explanation, which we retrieve then from an LLM. And they say that kind of worked well for a smaller set of information. However, it had declining accuracy in the generated queries once the complexity of that SQL and tables and the more tables and more information, then it didn't really work well. So they tried to improve. First of all, they understood that they need a better retrieval augmented generation to get relevant details once the data is a bit more complex. So, for example, they are saying that indeed, actually, retrieval augmented generation on the SQL queries doesn't really work that well and doesn't return relevant results. I also wonder if, depends on the embedding models they use. I don't know of embedding models which are trained on SQL queries, but maybe there are. Then also they found it challenging to understand users' intent. So they understood that they needed an intermediate step which would translate the prompt from the user into the intent of the user, and then using that intent they would be able to retrieve schemas and samples. And also they had issue handling really large schemas. So they are saying that some tables would have 200 columns, and this would totally take a lot of space, a lot of tokens for the large language model. So sometimes it actually would break that LLM call because it supports like less number of tokens. So taking into account those challenges, they created a new design, and they made some changes. First of all, they introduced workspaces, and workspaces generally business domains. So there are like a workspace for ads, for mobility, for core services, and they have kind of a more common business domains and also some custom business domains, or however they are calling them. So they have 11 system of workspaces, and then they can take a query, for example this one, write a query to find the number of trips that were completed by Teslas in Seattle yesterday. They take this query and they map to one of the workspaces, and then they know what kind of tables and what kind of approximate SQL queries they might want to write. For this, actually, they use this intent agent, which will take that query and then map to one of the domains. And this will narrow the search radius for retrieval augmented generation. So now they will be able to use less of the tables, columns, queries to find relevant stuff from their data set. Then they also have a table agent, because apparently they ran into an issue that query GPT was not always correct when picking up the tables to send the request. So they introduced kind of the step where they show to the users what tables will be used, and then a user will click looks good or will have to correct the tables to be used to send that query. Then another interesting thing which they introduced is a column prune agent. This is exactly to tackle that problem of having too much information in the database, too much mass and too much unnecessary columns and parts of chunks of data which they don't need. This column prune agent actually takes out all those irrelevant columns and saves a lot of tokens and prevents the token limit issues. Now, coming back to the article by Adnan Masood, he shares a couple of more examples of solutions which are worth noting. One of those is Dean SQL. So this is actually not a model, but rather a prompting strategy that can be used, which relies on a chain of thought decomposition and also includes a self-correction loop. And all of that gives a big accuracy boost to the solution, and when evaluated on the benchmarks, it actually gave a good results. So the BERT benchmark had 55.9 execution accuracy. So we have seen that actually right now the latest solutions get 77%, but this is kind of with the models, they get better and better with the tasks. Also, some models kind of cheat because they are usually trained, or like they sometimes trained on those benchmarks. In any case, this is an example of an autoregressive reasoning engine that can be directed with intermediate step and corrections. Then we have a SQL coder, and this is a set of models, large language models, fine-tuned and dedicated to the task of converting natural language into SQL. And this shows that specializing a model is a very effective way of solving this particular challenge. And these models seem to outperform even GPT-4, and they have 93 accuracy on unseen schemas and questions, and they were trained on a hand-curated dataset of SQL generation tasks. Now, in general, about architecture or architectural trends, the author states that nearly all top performing approaches utilize a transformer architecture. And also, they often use a graph neural network or specialized attention layers within that model for schema encoding. So this is how those models get information about the schema from the database. Then another trend he mentions is hybrid autoregressive decoding method, which generates a result from the model, so the SQL query, left to right with search or constraint checking. So here we actually, whenever we are producing that result, there is some kind of a feedback to see if we are moving into correct direction. Then he also touches on the complexity of the query. So he gives a couple of examples. The first one is pretty simple, where we just care about one table. And the second example is where we are talking about multi-table, which has also the query should use grouping and filtering. And obviously the second example is significantly more challenging, especially if, for example, here the question itself does not explicitly mention the names of the table, so the model must infer those names from the context. So with that, models need to use a combination of schema description, parsing, and learned context to make these schema linkages correctly. And all in all, good news is that we do see accuracy gains. Models are doing better and better. So when we look through the benchmarks and through the evolution of the models, so we look at the spider, we look at bird, so models generally score higher and higher when they need to translate natural language to SQL. However, there is still a gap when we are talking about more complex situations with more tables, more columns. In those situations, still models struggle a bit. So to make sure that we are not comparing the SQL itself, but we are comparing the result, the benchmarks sometimes emphasize execution accuracy. So they check the output of the generated SQL with the expected answer. And again, here there is information that the top models in those benchmarks, they achieve high 80s and lower 90s on easy queries and slightly lower scores on the hard ones. And this is a significant boost when we compare to 2019 models and solutions, which were reaching to only 40s on some easy tasks and 20s on more complex. So having 80s and 90s is significantly better. Inference speed and latency can be a challenge depending on the use case which you have. For example, for Uber, it was not really a problem. They still consider that 3 minutes versus 10 minutes a manual creation of those SQL queries is actually a win. However, there are solutions where you might want to have a smaller model which is fine-tuned so that it runs faster. And when it comes to the challenges and limitations, here we have a similar situation as from the paper. So the ambiguity in natural language is a problem. Handling synonyms and variations, complex and nested queries, multi-tables joins and schema complexity, domain adaptability and knowledge, SQL dialect and system mismatch, real-time performance constraint, silent failures and reliability, where the model can give a confident but wrong query, which sucks, security and ethical concerns, maintaining currency with schema changes, So all these issues, they exist. So you still cannot 100% trust LLM to create a correct SQL. Bunch of benchmarks here as well mentioned, which we can use, including the bird and the spider, to evaluate large language model. And we can expect only more solutions to emerge to tackle this problem of text into SQL query. And I'm looking forward to see how the field evolves. And hopefully, very soon, we will be able to use LLMs to write SQL and trust those models completely. I'm not sure when it will happen, but at least we are moving into the right direction.